Hello everyone, in this video we are going to discuss about periodic trends in chemical properties, and especially we will be discussing about periodicity of valence or oxidation states from the chapter 3 classification of elements and periodicity in properties, class 11 chemistry. You see, periodicity of valence or oxidation states refers to the recurring patterns of valence electrons and oxidation states in elements across the periodic table. The valence of representative elements is usually, though not necessarily, equal to the number of electrons in the outermost orbitals or equal to 8 minus the number of outermost electrons. For example, if you consider the group 1 element sodium, its atomic number is 11, so its electronic configuration is 1s2, 2s2, 2p6, 3s1, that is 281. So you see number of valence electrons, that is equal to 1. And what about valence? Valence will be equal to 1 or 8 minus 1, which is equal to 7. So valence for sodium is 1 or 7. But typically we consider 1 as the valence of sodium. Similarly, if you consider the group 16 element oxygen, its atomic number is 8. So its electronic configuration is 1s2, 2s2, 2p4, that is 2, 6. Okay, so here the number of valence electrons, that is equal to 6. And what about the valence? Valence is equal to 6 or 8 minus 6. 8 minus 6 is equal to 2. Okay. So you see, valence actually focuses on the number of electrons involved in bonding. Oxidation state emphasizes the charge on an atom in a compound. Valence focuses on the number of electrons involved in bonding, and oxidation state emphasizes the charge on an atom in a compound. See, nowadays the term oxidation state is frequently used for valence. Let us consider two oxygen containing compounds. One is OF2, another one is Na2O. OF2, that is oxygen difluoride, and Na2O, which is sodium oxide, that we will discuss later. So let us consider this let us consider this oxygen containing compound OF2, that is oxygen difluoride. Okay, now if you consider another one oxygen containing compound, which is Na2O, that is sodium oxide, you see the three elements involved in these two compounds are sodium, oxygen and fluorine. So the electronegativity of these elements are in the order of electronegativity of fluorine is greater than that of oxygen, which is greater than that of sodium. Okay, now let us consider this compound OF2. See, here oxygen has 8 atomic number. So its electronic configuration 1s2, 2s2, 2p4, that is 2, 6. And fluorine has atomic number 9. So 1s2, 2s2, 2p5, so 2, 7. That is the electronic configuration. That means oxygen has 6 valence electrons and fluorine has 7 valence electrons. So what it usually do in a compound is, when it forms OF2 compound, you see oxygen has 6 valence electrons, fluorine has 7 valence electrons. So each of the atoms of fluorine with outer electronic configuration 2s2 2p5 shares 1 electron with oxygen in the OF2 molecule. Okay, each fluorine shares 1 electron with oxygen atom. Since fluorine is the highest electronegative element, it is given an oxidation state -1. So the oxidation state for fluorine is -1. Oxygen with outer electronic configuration 2s2 2p4 shares 2 electrons. Okay, oxygen shares 2 electrons with fluorine atoms and exhibits an oxidation state +2. Okay. Now, let us consider the other oxygen containing compound sodium oxide, which is Na2O. See, sodium has atomic number 11, electronic configuration 1s2, 2s2, 2p6, 3s1, that is 281. And oxygen, its atomic number is 8, so 1s2, 2s2, 2p4, that is 26 is the electronic configuration. You see, so when this Na2O compound is formed, sodium has 1 valence electron, outermost electron is 1, and oxygen has 2, 4, 6 valence electrons. Okay, see, oxygen is more negative, electronegative than sodium. So oxygen accepts two electrons, okay, one from each of the two sodium atoms. So oxygen shows an oxidation state -2. See, oxygen is more electronegative than sodium in the Na2O compound. Oxygen accepts two electrons, one from each of the two sodium atoms. So oxygen shows an oxidation state -2 in the Na2O compound. See, in the OF2 compound, the oxidation state for oxygen was +2. But in the Na2O compound, the oxidation state for oxygen is -2. Okay, and the sodium with electronic configuration 3s1, it actually loses one electron to oxygen and shows an oxidation state +1. Okay, sodium, it has an electronic configuration 3s1, one electron in the outermost orbital. So it loses one electron to oxygen and shows an oxidation state +1. Thus, oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of the electronegative considerations from other atoms in the molecule. See, if we consider the periodic trends of valence electrons, it actually increases from left to right across a period and remain relatively constant down a group. That is, if we consider the periodic trends of valence electrons, it increases from left to right across a period and it remains relatively constant down a group. Okay, it remains relatively constant down a group. See, oxidation states show periodic variations with metals typically exhibiting +1, +2 or +3 oxidation states. Non-metals typically exhibiting -1, -2 or -3 oxidation states. Metalloids exhibiting variable oxidation states. See, the periodic trends in valence of elements as shown by the formulas of their compounds are shown here. So you see here we have the group formula of hydride. These are the first group, second group, 13th, 14th, like that. So you see periodic trends in valence are evident in the formulas of compounds including hydrides. That is, for group 1 elements, valence is 1. For group 2 elements, valence is 2. For group 13, valence is 3. For group 14 elements, valence is 4. For group 15, valence is 3. And group 16, valence is 2 or 6. Then for group 17, it is 1 or 7. So if you consider the elements down a group, that is the compounds, lithium hydride, sodium hydride and potassium hydride, their valence is 1. That is almost a constant down a group. The same thing is for the formula of oxides. Okay. And you see the transition elements and actinoids, they exhibit variable valence. So in this video, we have just discussed about the valence and oxidation states. I hope it is clear to you. Thank you.